this here, or I can just move things over. So I'm gonna have to orient, hello. I'm gonna have to orient my MacBook here. Oh, that's not too bad. So, ooh, perfect today, actually. Get a little wider area. So I'm gonna quick get this so we can see as much as we would like to. I'm actually gonna move it in today, hopefully. Hello. Because yesterday, if you watched, or if you watch it later, I had to write pretty big for you to see it. So today, hopefully, if we zoom in a little bit, plus there's less me and more board. Here we go. So I'm gonna quick move my borders. All right, so this one, this way, can go here. I know probably stuff I should figure out before I go live, but I don't care. I'll have to get rid of that. Don't need to worry about what that says. Okay. So I stay within the margins here. I have students watching me do this right now. They're here this morning. Again, freshmen are taking a state test. So my wonderful, here we go, my wonderful sophomores, juniors, and seniors are here. I'm going to just say who's here while I move my borders around. I won't say last names because it has to be secret. Oops, I cannot make this T go straight. There we go. Okay. So over here, way over here, actually over there, is Anna. Then next to Anna, this is more for me if I were check and watch this again, or other AP students in the future watch this. We have Olivia. And then we have in the front now, Dane and Troy. Again, they were here yesterday. So they were really sticking with it today, which is good. And in the front, we have Abby. Abby was here yesterday, too. Looks good. That looks good. And then we have Kylie again, and Richmond. Eli, who actually came through very well on the microphone for my cheap MacBook here. Not really cheap, I shouldn't say cheap. But the MacBook. And then Josh is here again. I'll ask Josh again how he's doing because I didn't get to intramolecular forces, and Josh does not know anything about that. And then Nathan's here again. We think that there's a ticking sound like on the first video. Nathan thinks that might have been him kind of flicking his pencil. I also got a cold, so hopefully my voice will not do what it's doing right now. I have tea though, so no coffee today. It's not good for you, I think, when you're ill. I have tea. I don't want to show the brand. I don't want to, unless you want to pay me money, I can show the brand. Kylie's laughing at that. Again, I can make better videos for this if I get 1,000 subscribers. This sounds pathetic, Olivia, but I don't really care how many more than 1,000. Just 1,000 is good. You could use a couple spares in case people leave. But then I can actually record with my phone, which I believe has better quality than this. So please subscribe. Let me have some tea first here. So I hope they're louder today and ask questions. They did laugh yesterday. So I'm going to have them try again. Say, hey, YouTube. They won't do it. But you'll hear them, hopefully, and hopefully they'll ask questions or catch my mistakes. So yesterday, I think I said one mistake that didn't get caught, and I don't know why anybody would know this. I think I said Hund's rule was somebody named E.L. Hund. It's not. It's actually Frederick Hund. That's the only thing. So I did watch mine back, and Eli caught mistakes, and who else caught some? They were little things. Richmond, too. They're human errors. There goes my voice again. Nathan's laughing at me. This is going to be fun today. So we're going to do intramolecular forces. They're all over the AP exam. I say they're like confetti. They throw it, and it lands on all these questions. So this is an important thing, and our wonderful Josh has no knowledge of any of these intramolecular forces. So we're going to do those first. And then we're going to move to all the math. So reaction stoichiometry, gas laws, solutions, all that. So there'll be 3 sessions again, about an hour each at most. I'm hoping my students ask questions today, and I hope I help out, okay? That's it. So let's go. Okay. So intra, I'm going to try to write bigger today. I found out yesterday I need to write bigger. So intra forces, let's just list them all. I'm going to ask them and see if they can answer. Josh won't answer unless he's just shooting at, guessing. So what's one intramolecular force? We'll actually list inter too. Intra right now. Intra. Okay. Basically it's a bond type. So these are intra. And I kind of sometimes say them wrong, but these are the forces that are within a molecule. Most of the time, people are just going to call these bonds. All right. Let's just list them like a normal person would. My students have a foldable of this. I don't know if anyone have them out. I'll try to grab one. Oh, we got one here. Hang on. Oh, it's not. Which one is it? Oh, that's good enough. We just need the choices. I won't open it. Eli says do not open it, okay? So inside of there, then they'd have the list of them, okay? So now I'm going to hide this. What are the forces that we can have inside molecules or between even ions? Give you a hint. Yeah, covalent bonding. And we're not going to have time really to talk much about these. To me, watch the other video on Vesper. So that's mainly your Vesper theory, your covalent molecules, all nonmetals, okay? Another one. Ionic, okay. Honestly, in AP Chem, I find that really the only thing that students have to kind of add in with ionic bonding is I think they know where the anions are, they know where the cations are. They really should have, you should have this memorized before you take the AP exam. I tell my students, really, it's not a good idea to show up unless you know your charges and your names of your ions. Some are polyatomic. Those make cations and anions, and then there are lattice energies that you need to deal with. I'm not talking about that. That is really something you can just read about. So do that, meaning what makes a lattice energy higher or what makes it lower when those ions come together and energetically bond, okay? It's kind of boring. I don't even want to waste time on it. Read about it, okay? Next one, what's another one? Yeah, metallic. So metallic bonding, again, not going to spend much time on that either. I'm just going to quick say kind of what to do. Really, the metallic bonding, you want to focus on, I talked about yesterday, delocalized electrons and why they give metals those cool properties that they have, okay? So again, read about it. You know, this is like, read all about it when they talk about it on a news thingy. Just read about it, okay? You don't really need it. I want to get to the math today. What's one more? This is the trickiest one. The covalent network. Again, this is another one where just read about it. These are your diamond, your graphite, covalent, sneak it in there, network. And then a lot of times if they call this one covalent network bonding, they'll call this one covalent, and then right here, because they make individual molecules, they'll call it covalent molecular. So that, again, that's a Vesper theory versus this is a huge, just like a computer network, this is a huge array of things. So the cool things are graphene and all the cool things happening in the world today. And at some point, if this video stays forever, those won't be cool anymore, it'll be something else. So this is kind of a cool area of science right now, I think. Interesting. So read again about it, those types of bonds that you have. They make them very high melting points and boiling points. They may or may not be conductive electricity, if that's the cool part about it. Metallic ones are obviously medium melting points, electrically conductive, thermally conductive. Ionic bonding, they're not conductive, but if you put them in a solution, they're electrolytes. And then covalent molecular are usually the easiest to melt, easier to pull the molecules apart. That's the intra force or inter force. So when they're talking about pulling molecules away from each other, that's inter, okay? I'm gonna mess up, I'm sick. The force inside the molecule, if you're Vesper bonded it, that's an intra, and that takes energy to break that bond, okay? So let me just draw something really quickly before we go to the forces, the difference. If this is my water molecule, okay, and here's another water molecule, all right, and they might have probably, this right here is called an intermolecular force. Whereas yesterday, when we talked, or in the other video, when I talked about the bonds that would be there, so we just kind of redraw it like this. So you've got a bond here, that's your hydrogen, this is your oxygen, and then maybe this one's coming out at you. And it's that bent shape. Let me get out of the way. This right here is an intramolecular force. And I think I might have even said this wrong. That you can break it and you can pull it apart. You can pull the molecule apart, but it takes bond energy to do that. And it's higher or lower depending on if it's single, double, or triple, okay? What I'm going to talk about today are the forces that are between these molecules. And for covalent molecules, the forces that are between them are always at least weaker than the force that is holding the atoms together, okay? So with these typically can be liquids or gases at room temperature. They can melt easily. They have vapor pressures and stuff like that. So those are things you wouldn't really talk about with these, okay? So that's where we're gonna focus really. We're gonna still focus on this set right here. But what we're doing today that's very different is really like yesterday was about this being a polar covalent bond. I'm trying to think what session that was. Must have been the last one, Vesper theory. So session 3. I got to rename this one. This one should be called 4. I just realized that. Oops. That is the force that's inside the molecule, okay? This today is going to be about the forces between the molecules, all right? So let's just list them and then I'll erase the board. So these are our intermolecular forces. And I'm going to kind of really say this one we got to focus on today, okay? So what are the forces that can be between molecules? Yeah, usually the strongest one, usually, let's say usually, is hydrogen bonding. And I actually call it a hydrogen bonding force. I'm kind of one of the few people that probably add that word. Because a lot of students think that this is the hydrogen bond. You can't really blame them. It's wrong, okay? But you can see why they think that. Actually, this right between a water molecule, because there's a hydrogen here, oxygen here, oxygen here. This intramolecular force I have listed here is going to be that hydrogen bonding. Whereas this is the actual bond, the actual molecular bond. All right, what's another one? Dipole. My students are sort of listing these in the tradition, as long as there's no exceptions, okay? They're listing them in the strongest to weakest. All right, at least for the forces that we have with just covalent molecules. There's one more for sure. Yeah, I'm actually going to say that one, I'm going to put it here. But really, if we were listing it, now this might bother some of you. I'm just going to erase this here. Ion dipole, I'm just going to call it number 0 because I want these in order. It's okay, we can have a 0. So ion dipole, and I'll show you what that is with the picture I've already got drawn. That usually people say that that's above hydrogen bonding. So for example, what would that be? I'm just going to use this water molecule. This is a negative end. This is the positive end of the water molecule. If I were to put like a sodium ion right here, the attraction between this positive ion, like that, and this negative end of this water molecule with these lone pairs right here, okay, in fact, we kind of go like this. This is the ion dipole force. That one has shown up actually a few times on the AP exam, so make sure you know that one. So it's just like if you had salt water, you'd say it has ion dipole forces. Okay, there's to me there's at least one more. Yeah, the London dispersion forces. And remember, this is still kind of about Josh today. He's like, please don't say my name again. But it is. So Josh, how are we doing? Kind of going nice and slow here. Good. I'm a little sick, so you're going to get a slower version of Mr. Schmidt today. And then really, let's put it here. However, to me, it kind of should be up higher. There is, let's just put it as like a star, maybe a special case. I hope you can see this. Oh yeah, you can't get it. Polarizability. Okay. If you haven't done that, or you don't know what that is, look it up and read about it. We'll go over it for sure. But that basically has to do with a molecule that has, and I always say about 70 or more electrons. They have what's called an induced dipole. These do. This is also called, a lot of people call these induced dipoles. It's momentary. So what happens with a large containing molecule of electrons, they induce their electrons from one side to the other, kind of like a wave, like at a stadium. and there can be a momentary negative charge that's really high on a molecule like that. And what happens is then it ends up, if they have that, they end up sometimes even being stronger forces between the molecules than even the elusive, I call it the elusive hydrogen bonding force. I would say that still ion dipole probably wins, but it gets pretty close. I could even say I could see people saying there's times where this polarizable LDF even hops up on top of that. And remember, these are the intermolecular forces, and then above here, those are all forces within molecules, and they're stronger. So if we had them all listed, we go back to, I just put the title. Did we have them in order? I don't think we did. So we should have had ion. Oh, we should have had covalent. What's the strongest intra force? Covalent network. Okay, I'm just gonna quick write them. And then most people agree second up is ionic. Third, usually people say metallic, and fourth, covalent molecular. So if you have them in this order, okay, you've got them from, like the strongest type of force up at the top to the weakest at the bottom. However, be careful. Polarizability can sneak up as the top interforce at times, okay? One last thing before I erase these. I'm just going to erase this because we don't need that for sure. Okay, read about those. I'm just going to leave just these. And I really won't talk much about the LDF because I want you to always understand that for every molecule or anything that has electrons, it always has which force? This one. You always list this one. If they said, what are all the forces? Not the strongest, but what are all? You always list LDF, okay? Then how do you have dipole-dipole forces? What do you have to have? You have to be a polar molecule, okay? So if it's a polar molecule, what you'll do is make a list, okay? So if you have a chart, make yourself a cute little chart that says, what do I put down? And let's just pick let's pick a flagship molecule for each one, meaning it's like a really common molecule of that type. So let's just do methane, okay? So I always tell my students, maybe build a chart and list, what's its structure, what's its polarity, and then what are its forces, okay? So it's going to be, what is it? What Vesper shape does it have? This is tetrahedral, like this, okay? So this is why that Vesper video, so session 3, says session 3 right now, but it's not. It's actually session 4. That's tetrahedral, and that is going to be polar and non-polar as a molecule. Yeah, so that's all equally distributed. You'd actually say like positive, positive, positive ends. So this is going to be a non-polar molecule, or you could call it has non-dipole. Okay, and then that means the only force that it can have is LDF. Now, if you want, add another column. I have just enough room. Count up the total electrons, not valence. Okay, so yesterday we were talking about valence a lot. How many total electrons are in methane? So carbon, not valence, total. I think it's 10, right, Dane? I want to keep checking with Dane and Eli are good checkers here. 10. And so what I said before was it has to have, I'll write this back down. It has to have, I think, 70. Okay. I'll put this one back. All right, let's do the next one up. So a molecule let's do one that has dipole-dipole, but not hydrogen bonding. So what elements are we trying to make sure we don't put in this molecule? What 3? We know. We want dipole-dipole. We don't want hydrogen bonding. We don't want an FON in here, okay? So just anything else that you can think of. It's just some simple molecule, easy. I'll just say HCl, okay? Something that if anybody was watching this, they would be like, oh, I know that. That's hydrochloric acid, okay? But we're going to say it's hydrochloric acid as a gas. meaning that it's molecular, not dissolved, not an acid in terms of like it dissociated. Okay, so be careful, those of you smarty pants that know that. What's the shape? It's just linear. And then this would be, if we were really using our model kits, this is getting kind of picky today, but I'm going to go slower because I'm not feeling so good here. You'd say that that's a green one. Yeah, that came through. That looks nice. So it's linear, okay? But it definitely has a positive and negative end if you were to draw the electronegativity. So keep in mind, electronegativity, that was, I think, actually our first video. Electronegativity is larger as you go to the P block over here and up. Okay, so chlorine has a really high electronegativity. We don't really care what the number is. And then what does it make that? Polar? Or it has a dipole. So I always tell my students, list that as a dipole, but call it a polar molecule because that's what they want you to say. So then what does it definitely have? Well, it has LDF. That's not the strongest force it has, but they may say, what are all the forces? If they say, what's the strongest force, you'll list dipole-dipole. Now, if you want, off the side, if we want to show one HCl attracted to another HCl, you would do this. And then you draw the attraction between them like that, okay? And this actually has 3 pairs of lone pairs, this chlorine right here. That's not really why it's got a negative end, it's because of polarity. So they're going to be attracted like that. This is your Cl, this is your H. Now the reason why this is not going to be a hydrogen bond is because you have to have a hydrogen bonded to an FON and attracted to an FON. Write that down. I tell my students they should already have written that down. Josh, did you write that down?
I will.
Okay. So it's a hydrogen bonded to an FON. I'll show you an example of how they caught a bunch of students one year. A lot of them got it wrong. Bonded to an FON and attracted to an FON.
FON is atoms.
And those are the atoms, people. Because they're probably like, what is she doing? Fluorine, oxygen, and nitrogen. Good catch. Oh my goodness. Okay. How many total electrons? And it really doesn't matter because it's really the LDF that have a ton of electrons, only LDF, but let's just do it. Chlorine has 17, so only 18. You still aren't making the cutoff. Okay, try to pick good ones here. Okay, now let me just draw the methane quick too. So if you had methane, because I'm going slow here. After this, I'll probably stop picking on Josh too. He'll be so happy. But after this, Josh has lots of experience with the rest of the stuff. Okay, so this is kind of where he's having some stress. And he knows, because we've looked at a bunch of FRQs and practice tests, he knows this stuff is on the AP exam. Like he's seen it enough times to say, I have to fill these holes. I'm going to take the test. Okay. So what I'm going to do is say draw like maybe these are a little bit bigger dots and show like they're a little more attracted. And then these, for a moment in time, there could be a partial negative end for a moment. Okay, so I'm going to put momentary. And there could be a partial positive end in just a quick moment. And then there's just this really weak, these little dots you might not even be able to see if you're watching the video. That's okay, perfect. Because it's fleeting. It's just gonna go away. And that's why this is typically what state of matter. So I'm gonna get rid of these forces because we can add some more to this table. What state of matter is methane at room temperature? We use it to light our Bunsen, with our Bunsen burner gas, right? So you may want to put like state of matter underneath here. At room temperature, gas. Okay. Now, this one, if it was pure HCl, it still would be what state of matter. Now, normal high school students wouldn't use pure HCl. I have TAs or chem club people that might end up, because we have to make hydrochloric acid solution. My hair's crazy. Holy cow. What state of matter is it? It can be gas, because you'll smell it when you open up the container, use a fume hood, get some goggles on, whole shebang. I mean, this is serious business when you use HCl. Heading off to college, some of you are going to use concentrate HCl. But it can be a liquid. Okay, so it's a gas or a liquid. Now, typically, what do we do with this one if we're going to give it to a student to use in lab? We're going to dissolve it in water and make a solution. Okay, so it's still sort of, it's a solution, but it's liquid phase. Okay. Be careful in chemistry, so that's really hard for students. Liquid means pure. And then aqueous is still like, like if you're little, you're still going to say it's a liquid, okay? But it's really a solution, okay? All right, next one. What do you think we should use? Let's use something different. I know they're going to say let's use water, but let's not. Let me think of another molecule that would be definitely hydrogen bonding. That's kind of common. It has a nitrogen, oxygen, or fluorine. I know Dana, I was going to say. You could use NO2. Yeah, there's a lot of them actually. There's a lot of good answers. I think I'm just going to go with just ammonia. How about that? That's a nice easy one. Like everybody, if they're watching this, they're like, oh yeah. These are the kind of things that, you know, first year chem, you probably ran into these. So we're going to draw it because I think we didn't get to, too many Vesper structures yesterday. I wanted to show you guys this. My students have a nice foldable, but remember we spent a lot of time with 4 regions. So I want to show this to you. Some of you probably have something like this, okay? So you got electronegativity table, hopefully, and then you've got this list. This list is what I was talking about yesterday that you need to have memorized for the AP exam. The name, the shape, the bond angle, the whole shebang. Anytime it's bent or pyramidal, chances are it's polar molecule. And then if it's really symmetrical, you just have to look for, is there something different on one end? If not, if it's symmetrical, it's probably nonpolar, okay? Those are not the best way to go about it, but it's a quick way to do it, okay? So we spent a lot of time on this 4 regions, okay? But there are other choices. Okay, keep going. So this is gonna be polar, definitely. It has a dipole. I'm gonna make this kind of nice today again, go slow for Josh. They always have LDF. As soon as you have electrons, you get to have LDF. I always say like LDF is like coming to public school. You just come, it's free, come on, come in. But gaining the other forces is sort of like maybe scoring well or doing something special where you get into a different group. Okay, I don't care if that's music or band or choir. Abby, help me out. Sports, varsity, right?
Buy money?
Yeah. Or even making the musical or something, like you're part of the lead role. Okay, so you get dipole-dipole because it's polar and dipole. Now, why does this one get to have, I would say, the elusive hydrogen bonding? I kind of pretend like that's like the Navy SEALs of the Navy here. So you've got your nitrogen here, your hydrogen's here. The whole bottom here is going to be partially positive. This has one lone pair here, so it's partially negative up there. But it's not because of the lone pair, it's because these electrons, if you drew the arrows, they're all heading up to the top, okay? And if you're getting really picky, if it's got, your positive end here, I'll just do that so you can see it, and then the negative end here. If I were to line up another one, I'm going to kind of turn it a little bit. This is where my art skills are going to lack here. Let's go like this. Oh boy, here we go. And then let's go this way. Don't judge here, people. You try to draw a pyramidal upside down. Oh no, that's wrong. What am I doing? You just draw it normal. What I was thinking here. Human error. Catch it myself before it gets too far. Okay, so you got your nitrogen here, hydrogen's here. Now technically, it's really like you can get really picky that you can only have like one. And I'm going to draw these as really big, intermolecular attractions. I'm going to get rid of the lone pair though. But there's that hydrogen bonding. And I'm going to write the whole word and go kind of slow here. Hydrogen bonding force. Because yesterday, I think that looks nicer today. I'm writing bigger, thicker color here. So that's the strongest. Be careful again. You have to say this. So I'm going to grab a different color. I think blue looked nice, so I'm going to stick with blue. Actually, let's leave that one out because I used that one. Here's what you need to check. Do you have, I'm going to color code this one. Do you have a hydrogen bonded to a nitrogen, oxygen, or fluorine? So NOF, because I was just saying NOF, but somebody might not know what that means. And then is it attracted to a nitrogen, oxygen, and fluorine? And the answer is yes. So this is why this gets to be the hydrogen bonding. I'm just going to put HB. How many total electrons? It's not really worth doing, but let's just do it.
10.
Yeah, just 10. And then state of matter, it can be gas or liquid again. Okay. All right. Now we want to have something that is kind of unique, and I'm just going to stick with something that I've seen happen before. It's I don't know why this is such a large section here. Let's do. Maybe I can find one more thing to put in here. But carbon tetrachloride, or carbon tet. If you go to college, they're going to call it carbon tet. So it is going to be Tetrahedral again. Okay. The only difference is you have a larger size chloride or what am I saying? Chlorine atom in the middle. So if you're color coding, that would be green. Okay. Wait, no.
Carbon.
Oh my goodness, the thing these students are here to catch my mistakes. I'm catching them before I get done here, but I think I had to take cold medicine too, so that's probably part of the problem. Blame it on that. So actually, I should probably draw these even bigger than hydrogens. So I'm spending some time here, Josh. Hope it's worth it, huh? Okay. Okay. So I want to even do it as best as I can that those are larger. Those are larger than a hydrogen. And that's your carbon there. Okay, so it looked like that. That looks not the worst. Okay, so then is it polar or non-polar? Non-polar, yeah. So the non-dipole, I'm just going to go ND, non-dipole, ND, non-dipole. Has to have LDF. Can have dipole-dipole, can have hydrogen bonding for lots of reasons, okay, but it can't. Number one, it doesn't have a fluorine, oxygen, nitrogen. It doesn't even have a hydrogen, so how's this going to happen? And then it's not a dipole, it's not polar, so it can't have that. How many electrons though?
Over 70.
Over 70, right? So 17 times 4, who's good at this?
68 plus carbon.
6, which is 74.
74, okay. And it kind of hit that, there isn't a rule out there of like what number. I just think 70 always has been pretty good about being right. So it's got 70 or more electrons. So even though it only has LDF, this is the one that is what's called polarizable, or it has polarizability. This also is a liquid at room temperature, unlike the other one being a gas. Okay, so I know it's not a drastic state of matter change at room temperature, but it is. So it's a nonpolar molecule that is a liquid, so it means that they're highly attracted to each other. So if you're going to draw two of these, I'm not going to color code because that's going to take too much time. But if I drew another one next to it, okay, and the AP test is very particulate. So if you think you're not going to be labeling or explaining any particulate views, you're wrong. Okay, you are going to see these on multiple choice and all kinds of stuff. I'm going to draw these really big. These are fairly attractive induced dipoles. Okay, so what happens again is for a moment in time, all the electrons shift to one side and it's partially negative for just a moment in time. And then maybe all of these start sliding this way. Okay, so there's a negative end over here and a positive end here for just, I'm going to keep putting moment. But that momentary dipole, that induced dipole for just a moment is so strong that it ends up being equally matched to having a true permanent dipole, okay? So water, ammonia, HCl have permanent dipoles, whereas these have a momentary dipole. I've seen this show up on the AP exam a lot, okay? So be aware of that. Watch, this or read about it if you don't have time, okay? All right, I think we're good. I don't want to do another one. We could do like an ion dipole if you want. Well, let's just do that. What would be an easy ion dipole? Just salt water, right? Just do like NaCl-AQ. And then what I would do is just write down, you've got an ion, you've got a dipole. That was the picture I had before. So you got your water molecule. And then let's just do a different ion. Let's say it's got chloride dissolved. There'd be a positive end and a permanent negative. So you'd have your attraction there. And then you would say that you could say LDF. You could say dipole-dipole. You could say H bonding. And then I put ion dipole ID. Don't worry about this. And then this, of course, is a solution. Solution S1. Okay? And that means that that solution is part of the stuff that solution's coming. Because we put the salt in there, you have elevated boiling point, depressed freezing point. Again, not on the AP test, but I actually think it should be. I'll put that out there. But it's not. So you don't have to calculate it. But I still think it comes up as an important thing to know. So those solutions now would have different melting points and freezing points and boiling points. Also. Okay. And vapor pressures too. So this would actually lower the vapor pressure of water. Water would have a certain vapor pressure at a certain temperature. And if I put salt in it, it would lower it. Okay. Are we doing okay? I'm going to take a break here. Josh, good? 34 minutes. I don't know. It's not bad to teach you really quickly intra, a little bit of intra and inter. Any questions that you guys have that have already kind of been through it? Anybody have the foldable that is the intermolecular forces handy? I'll just grab that. Eli's got a question. Go ahead. I'll be right back. What's your question then?
Why do you not have to worry about lone pairs on
Oh, so it's a good question. Let me show you this first. And sometimes this year I think I made this bigger, but they basically have them, and I think they listed them in order now. Her ion dipole, oh, she's got it in the back. Fantastic. And then she has ion. So that's where we turn into kind of an ionic bond. So we can kind of take that one off. So you got ion dipole, and then have these. And then on the inside, if she's okay with me opening, yes, a big reveal. They'll put all their notes and drawings on there. So right now, most of the students I have sitting in here for 30 some minutes are just kind of like, yeah, I got all this. I'm just refreshing it. But again, this is for Josh. And maybe many of you, I know when I first started teaching AP Chem, I didn't want to teach this. Guilty. But then it became very popular. Like in 2007 to 2014, it was like, this is a big deal. Start really teaching this. I think because there's no math. This is, again, I picked on Josh's teacher, who he had before. Very mathematical. And I think if you're not mathematical, you kind of avoid all this artsy. It feels artsy, like because you're drawing stuff. So let's go to Eli's question. I'm just going to see if I can hand this to Abby. Oh, good stretch. Okay, so what he asked is why does the lone pair not really matter for polarity? So for polarity, I know this is a big thing, but just trust me, I guess, until you can get some physics. For polarity, what you're really worrying about is hydrogen has like a 2.2. I don't know what nitrogen's electronegativity is. If you really want the exact number, you'd find a chart. So on this one, it says nitrogen's 3.04. Let's just say 3.0. So what you'll do is you'll take and you'll draw an electron arrow, sort of saying that the electrons are going up to the top. And what I tell students to do is draw them on top of there, but also kind of pull them off. This is good for Josh. And draw them like you would maybe in physics as vectors. And you can see that there is a net movement of electrons going up to the top. So yeah, there's a lone pair there when we drew the dot structure, but it's really about the influx of electrons being pulled towards the top. So then what you'll do is you'll say this is what causes this molecule then, if all these electrons are going this way, to have a permanent negative here, and a permanent partial positive. But it's still partial. That's called a delta sign. You see that with red? Yeah. Does that help, Eli?
Yeah,
a little bit, but yeah.
Because you're saying that it's stronger.
Yeah, what I heard one time was that you can't draw, it has to do with, I think, Eli, let me say this, I think this is important. And this is like 4s and 5s kind of students. What I heard one time was if I drew two, these are the lone pair dots, okay? I'll draw these as a dash. You can only draw one dash going to that. So what some students were doing one year is they were doing this, Eli. They were kind of going like dash crazy. They're like, look at all these hydrogen bonds. If there's one lone pair, you can draw one set of dashes. If there's two lone pairs, you could draw two set of dashes. Does that make sense? So, and that's very nitpicky, but it is kind of a big deal, I think. Not enough, to make you probably get huge punch points. So with water, like with this one, I could draw another HCl next to this one. And if I were drawing this with dashes, I'd go dash, dash, dash. And I could add another one right here, Eli. Does that help? And I could put a third one. Because this one has 3 lone pairs. So that's what I was blabbering about. You're going to have to check me today because these are lone pairs. And then like that. Does that help? So we could draw 3 of them. This is totally like, no, sorry, it isn't that. It's not that. It's not that much hydrogen bonding. There's some tea. How are we doing? Doing good. Okay. So, here for this. Does that help? Does that summarize it pretty good for those of you that are just kind of reviewing and learning it? Because it's a lot. It is really important. So I think we're at like 30 some minutes right now, Josh, but I think it's worth it for that. So we're just going to kind of wrap this up, and I'll just have to call this my intramolecular force. Let's just even see if it showed up on the AP exam last year. And because I gave my students like the example copies from my students, we can always look this up. I'm not telling you anything you can't find on the internet. You can find all these FRQs on the internet for response questions. You can freely respond to any of these questions, which some students definitely do. I'm trying to see where we could have like an IMF type question. There it is. I found it. It's typically somewhere on the FRQ. So here's where it is. I don't know who I stole here. Hopefully it's a good answer. I'll try not to show their work. We won't say their name. This is somebody last year that I had in class. So there's the question. Again, I'm not showing you something you can't find. Go on the internet, people. You can find these. The first question says the table table above, so they put boiling points. Okay, so unlike me, I just put gas and liquid and stuff. They'll have legitimate data. It says the above data gives molecular structures and boiling points for CS2 and COS in terms of types of relative strengths of all intermolecular forces in each compound. Explain why the boiling point of CS2 is higher than COS. Okay, what did my student write? Like, let's just read it quick. The intermolecular forces of CS2 are stronger than those of COS, which explains for the higher boiling point. They both have the same number of valence electrons in nonpolar linear shape. So I don't think they got it. Okay, I don't think they got the point. What are they looking for? Do you guys know what they're looking for? What are they trying to get at? CS2 is linear. COS is linear. Yeah. Well, you got that. That's not helping at all, okay? But CS2 has a higher boiling point. What are they really trying to get you to see? One's polar, one's nonpolar. Who's polar, who's nonpolar? That one is actually nonpolar, and that one is polar. So you'd predict that this one would have the higher boiling point, but it does not. So what are they looking for? It's that stronger LDF forces, the polarizability. Did anybody have a paper that said that? If you look it up on the internet, I hope that's right. We're looking at 4A. You know, and this is what's called a 4-point question. So it's 2 points for A probably and 2 points for B. I can't go on the internet because I'm taping this live and this is my computer. I don't know if there's no way for me to do that. I'm not that cool. But I would love to look up what the accepted answer is. But my guess is it's polarizability of LDF. So anyways, look it up, okay? Because I think that's what I was just blabbering about with the 70 electrons. Does it have 70? So 16 plus 16 plus 6 is not 70, but it's larger. And then COS should be less. So yeah.
COS also usually weak dipole, but doesn't seem like to be that strong.
Yeah, and he's saying it's like the weak dipole that exists must not be as strong as the.
Well, just the dipole itself
is weaker.
The strongest polar molecule.
Yeah, it's not very strong polar molecule. So we'll have to look on the internet. You do that, okay? Yep.
Well, I did look it up, and the answer says that CS2 only has London dispersion forces, while COS has London dispersion forces and dipole forces, and that the London dispersion forces in CS2 are stronger than the combination of LDF and dipole and COS.
Good. So it is. It is that, and they didn't have to say why. They let the students get the point as long as they said, I don't know why, but it's definitely the LDF forces in CS2, which typically are not strong, but they are obviously this time. So they didn't need to say the polarizability thing or the electron count, but I would add it in there just in case. But they just had to say it is. I don't know, it's the way it is. But you had to clearly state, I think, the forces in both, and then just say the LDF was stronger.
It was 1 point for identifying all of the.
Oh, all the forces. So do a table like this, okay? So identify all the forces, and then you would say this LDF must just be unusually strong compared to, if you're comparing it to this one that has, or even this one, maybe the boiling points, who knows? So that's what you want to do, okay? So we did find it. I think we're going to call this a wrap. So it didn't seem like a lot. It's a lot of time, but I think it is important, okay? So look up some previous exams. I think you're going to find these intermolecular forces on every single FRQ for a long time, since probably 2007, 2014. So I'm going to say CNR. This is going to be session 4. I'm going to go to 5 and 6, which is going to be a lot more math. And then we'll be good. So we're going to take a break. See you later. Good luck. Hopefully if you watch this again. Ooh, Kai's got a question quick.
No, I just want to answer on this.
Somebody answered on there that was good?
Possibly.
Oh, here, bring it up here. I'm going to read it quick. So if you don't want to watch, stop watching now. But I'm going to see if I had a good one in the bunch here. So let's see. Ooh, pretty handwriting too. So this is one of my students. Okay, so CS2 has a higher boiling point than COS because CS2 has stronger intermolecular forces, which means the bonds are harder to break. Requiring more energy. CS2 is dipole. Okay, stronger. So my guess is this one actually is pretty close, but this is something we see. So this is actually a good learning thing. My advice is don't say this thing about breaking bonds. Okay, when you write this breaking bonds part right here, this is what a reader could think you're saying, okay? They think you're meaning breaking this bond right there, okay? So don't say breaking bonds unless you really mean bonds are broken and you're doing like thermochemistry. Bonds broken minus bonds formed, that kind of thing. Got it, Josh? So don't even put that in there. So don't say bonds breaking. You could say molecules being don't say pulled apart either. Say molecules being, this one being moved over here and this one being moved over. I don't know how you want to say it, that you don't say anything about breaking the bonds, okay? Does that make sense? That's a good one to say. So this was pretty good, but I think they probably fell short too in terms of that. Let's send that back here. Here you go. But yeah, so be careful. Make sure you somehow clearly state that if I have a molecule here, let's just draw water, and I have a molecule here, that what I mean is I'm separating the molecules from each other, not separating the molecule. Does that make sense? So, because it sounds like you're a politician, you're writing a speech, you don't want to get somebody's interpretations different. So be careful. You never want to make it sound like you're breaking off, Mickey Mouse's ear off of the water. Because now what is that, people? AP Chem knows this. That's hydroxide now. And this is water. That's totally different because now what's going on? Well, now we have hydrolysis of water, and that's completely different than what we really meant to say.
Oh, this is
Sound a good one? Okay. All right, should we go? Should we read it quick? Eli's voice, usually you can hear him.
CS2 contains LDF forces. COS has dipole-dipole forces. In general, dipole-dipole forces are stronger than LDF forces, but in this case, CS2 is larger than COS, and the LDF forces it contains are stronger than the forces of COS. Stronger intermolecular forces lead to a higher blood.
Yeah, pretty good. I don't know if because they didn't say that the one has
COS has
both.
dispersion.
Has LDF and dipole-dipole. I would hope that one got through, but you're right, Anna, with the way that said it, they didn't say, they didn't say it all. So make a chart, okay? And then list them all. Okay, we're good. Off we go, snack time for us and a break. More tea for me. Bye. Hopefully my DECA students who are heading to Florida will watch this because you need review. Some of the things we said here are really important. This is how you lose points or gain points. Good chemistry is still kind of sitting there, but you got to say it the right way to get all the points. All right.